This is my Calculus 1 course. Today we're going to do some pre-calculus review. You should have your binder and all the other materials that we talked about in the first class. If you don't have those materials, you can't organize your work. So make sure that you have that stuff. Pre-calculus review is traditionally a significant portion of your first calculus course. But I'm not going to make pre-calculus review a big part of this course for a number of reasons. One reason is it's impossible to review an entire pre-calculus curriculum in one course. So it's just not possible to do that. Also, students typically want to get right into the calculus, so I don't want to bore you with a lot of pre-calculus review. Also, the purpose of this class and the next class is not really to review pre-calculus because, again, that's not really possible to do in one calculus course. The purpose of this review is really to give you a warning about the things that you're expected to know. We're going to go over some basic principles that you should have learned in previous courses, and if you find that you don't know some of these principles, then that's an indication that you either did not finish their prerequisite courses, or the instruction that you got in previous courses was not sufficient. Every K-12 math teacher is an expert when it comes to the math curriculum, but what you find when you take your first calculus course is that many of those teachers really were not experts when it came to the math curriculum, because when it comes to some of the fundamental things that you should have not only learned but focused on, you find that some of these things you either did not learn or you just didn't learn in enough depth to be ready for upper math courses. So oftentimes calculus students become frustrated and upset in their first calculus course because their teacher doesn't explain the things that they were supposed to learn in previous courses. And I just want to avoid that. I'm going to let you know in this class today and in the next class what you're expected to know. We're not going to go into these things in depth because this is all stuff that you should know before taking calculus. That's why math prerequisites are strictly enforced. So the exponent rules is a perfect example of that. When you look at each one of these topics, it's very common for students to not really know this stuff as well as they should, because it's the math curricula in the United States and around the world just isn't really taught in a way that prepares students for upper math. And again, that's something that students unfortunately have to figure out when they first take calculus. So if we start to review this stuff and you find that you have never seen some of these topics, that's a sign that you didn't really learn what you needed to learn in previous courses. If you find that you're a little rusty on some of these topics, that's completely normal. But again, if you find that you're hopelessly confused or you've never seen this stuff, then that means that you're in the wrong course. If you're coming from my curriculum, then you don't really need to worry about it. As long as you did all the homework and pass the tests, you're fine. But if you are coming from a different curriculum, you can always take my courses. That's why I designed those courses, is so that you can have a guarantee that you're ready for upper mathematics. So we're going to start with the exponent rules. The exponent rules are crucial. They are one of the many things that are absolutely crucial when it comes to your ability to move up into upper mathematics. So get a picture of these rules. We cannot proceed unless you have a picture of those exponent rules. So we're going to simplify these expressions, and I don't want you to leave your answers with negative or fraction exponents. And this is going to demonstrate the exponent rules that you really need to know. You're going to be expected to know these rules, and your calculus teacher is not going to explain them. This course is all about learning calculus. It's not about learning, algebra or trigonometry or geometry, so on and so forth. Now, if you know how to do this, you can get it done in less than 10 seconds. And you can go ahead and do the problem. But I'm going to show the steps, and I'm going to write the Roman numerals of the rules that we're using. So first we're going to use exponent rule number 1. We're going to multiply these powers because they have the same base. And rule number 1 tells us to add the exponents. I'm also going to use exponent rule number 7 because anything raised to the 0 power is just 1. And I'm going to use exponent rule number 6, which tells us that x can be written as x to the first power. So we used 3 rules in the first step. That's rule number 6. And we also used rule number 1. Okay, and we can't forget to write the negative 2/3, b to the negative 2/3 power. Let's double check, make sure we did everything correctly. We forgot the a to the 4th power, so it's good to double check, make sure we have everything. So now we can use exponent rule number 2. And that's because we're dividing powers. So when you divide powers, you subtract the powers, or subtract the exponents. And I'm going to also use exponent rule number 8 in order to get rid of that negative exponent, or convert the negative exponent. Then we're going to use exponent rule number 4, which tells us that when you raise a fraction to some power, that expression is equal to the numerator of the fraction raised to that power divided by the denominator of that fraction raised to that power. I'm also going to use exponent rule number 10 to change that fraction exponent to the cube root of b squared. Now I can also write that as the cube root of b all squared. Remember, there's 2 versions of exponent rule number 10. So you can write it this way or you can write it this way, but generally it's preferred to write it this way because we don't want to have to write parentheses if we don't have to. Okay, so now I'm going to multiply the fractions, and I'm also going to use exponent rule number 3, which tells us that if you have a product raised to a power, that expression is equal to the first number in the product raised to that power times the second number in the product raised to that power. And I'm just going to keep the denominator in that form for now. And I'm going to go ahead and multiply the fractions together so we can put it into one, write the expression as one fraction. Okay, so now I'm going to use exponent rule number 5 because we're raising powers to other powers. So in that case, we're going to multiply the exponents, and we're done. Now, often, students may say, well, wait a second, we have a root in the denominator. We're not allowed to have a root in the denominator. Well, we could rationalize the denominator, but to be honest with you, that takes a lot of weird algebra, and usually teachers will just skip that. You can usually just keep your answer in that form, and that's because we have a variable inside the root, and it's a cube root. So again, those are things that typically we don't really worry about unless it's just a square root of a regular number. Okay, so now I want you to try a problem like that. I want you to attempt number 2, and if you want to write the Roman numerals of the exponent rules that you're using, you can do that here, but you don't have to write the Roman numerals. You don't really have to show the steps at all. If you know what you're doing, you can get the answer in 10, 20 seconds. We're just showing the steps just to help you review this this work. So go ahead and try number 2. I'm going to give you one more chance to take a picture of those exponent rules. So I want to emphasize that the purpose of this is not to teach you this material. You should already know the material. We're simply reviewing the material and giving you an example of the things that you need to know. So try number 2, see what you can do, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. So I forgot to use colors on some of these steps because it's kind of hard to do that, but obviously you don't have to use colors, you don't have to show every step, you don't have to show the Roman numerals. We're just being thorough here. So let's try another problem. We'll just do a couple more of these. Now one purpose of this class is just to help you get your mind jump started, to get you into the math. Again, even though we learned this in my curriculum, you may not have looked at some of these rules in a while, so that's what we're doing here. So we can use exponent rule number 4. We're raising a fraction to a power. And we can use exponent rule number 7. And also number 2. So for number 2, we're going to change those b's to b to the 3rd power. And for rule number 7, we're going to change 2m to the 0 power to 1. Anything raised to the 0 power is just 1. We can also use exponent rule number 1. So we use 4 rules in the same step. So we're going to multiply those a's, and exponent rule number 1 tells us to add the exponents when you multiply powers. Okay, so let's double check this, make sure we did everything correctly. You always want to double check because it's very easy to make a mistake. Okay, everything looks right. And what was exponent rule number 4? That was this here. Okay, so now we can use exponent rule number 9, which is a rule that we have not used yet. And that is going to change the cube root to 1/3 power. So that's where that purple came from. That's all raised to the 1/3 power. So the only real difference is that we could have written all of this to the 1st power, and that's where the 1 came from. Or you could write the inside part to the 1st power. That's where the 1 could have come from. It's just kind of a different version of exponent rule number 10. So let's make sure we have everything correct. That looks right. So now we're going to use exponent rule number 4 because we have a fraction raised to a power. Exponent rule number 4 tells us that that expression is equal to the numerator of the fraction raised to that power divided by the denominator of the fraction raised to that power. And so that was exponent rule number 4. Again, you don't have to use colors here. It's kind of tedious to have to do that. Now we're going to use exponent rule number 5. And that's to multiply, or that tells us when you raise a power to another power, we're just going to multiply the exponents. Okay, so now we're going to use exponent rule number 2. We're going to divide the b's, and when you divide, you subtract the exponents, so we get b to the negative 9th. We're also going to divide the a's, and when you divide powers, you subtract the exponents, so 10 minus 8 thirds. So you can do that however you want to do it, but regardless of however you do it, that's going to give you 22 over 3 for the exponent there. So now we just need to get rid of the negative exponent. Well, actually, we need to get rid of the negative exponent, but we also need to get rid of the fraction exponent. So we're going to use rule number 8 to get rid of the negative exponent. And we're going to use rule number 10. Looks like we're going to use rule number 10 again. That's going to be the cube root of a to the 22nd power. So that was number 3. Alright, so I want you to, again, I'm going to give you a chance to get a picture of the exponent rules, and I want you to get a picture of problems 1 through 3, and I want you to do number 4. So again, the purpose of this is not to teach you this material. The purpose is to review. You should be fairly well versed when it comes to this. If you're a little rusty, again, we're going to get your mind jump started. So you don't have to show all the steps. You can do this quickly if you have the ability to do that. You don't have to show the Roman numerals. You don't have to use highlighting. You don't have to do any of that stuff. You can do this in 10 seconds if you want. So you know, take as much time as you need, or do it quickly. It's up to you. The purpose is just to get your mind jump started. So try number 4. When you come back, we'll do it together. Okay, we're back. So if you got that answer, good. Okay, so again, the exponent rules are absolutely crucial. It's something that teachers really need to focus on a lot in K-12 mathematics, but unfortunately, they don't. They don't really focus on it much in most cases. Some teachers do, but a lot of teachers don't focus on it, and so students don't really, they're not as fluent when it comes to that. But that's something you're going to be expected to know regardless of whether or not you learned it in previous classes. So now we're going to review the distributive rule a little bit. So the distributive rule means that if you multiply a sum or a difference by some number, then you can just multiply each term in the sum or difference and then add the corresponding terms. So 3x times x is 3x squared. 3x times negative 2 is negative 6x. 4y squared times 10y to the 6 is 40y to the 8th. 4y squared times negative 9y is negative 36y cubed. And 4y squared times 1 is 4y squared. So we're not really going over this in a lot of detail, because this is stuff that is really just most students at this point are going to know how to do this. So I want you to try number 7 and 8. Again, the purpose of this is just to get your mind jump started. So try number 7. When you come back, we'll do it together. Okay, we're back. So we have 16x to the 8th plus 24x to the 7th. You got that right? Good. So go ahead and try number 8. When you come back, we'll do it together. Okay, we're back. So we have 7, or negative 7, b cubed plus 35b squared minus 49b. So have you got that right? Excellent. Okay, so now we're going to multiply binomials. This is also something very, very basic. So basic that we're just going to, move through this very quickly. Again, the purpose of this is not to teach you the material. You should already know this. The purpose is just to get your mind jump-started and to remind you of a few things. So when you multiply binomials, typically we use the FOIL acronym to help us. Now, you may have learned the box method. X plus 6 times x plus 4, and we get x squared, and 6x, and 4x, and 24. But that method really is not very practical because you have to draw a box. We don't really want to draw a box every time we do this. So typically the FOIL acronym is used. Again, FOIL. So FOIL stands for the first terms. We're going to multiply the first terms. X times x is x squared. Then we're going to multiply the outside terms, and we get 4x. And we're going to add all these terms together, the resulting numbers that we get. Then we're going to multiply the inside terms. That stands for I. 6x. Then we're going to multiply the last terms, and we get 24. So notice these terms are like terms. So we're going to add those up, and we get 10x. And that's how we multiply binomials. So let's try one more example before you try one on your own. So here's a product of binomials. We're going to multiply the first terms, and we get 6y squared. Then we're going to multiply the outside terms, and we get 22y. Then the inside terms, we get negative 3y. Then we're going to multiply the last terms, and we get negative 11. Okay, then we're going to combine the inner terms, and there we go. So you got that right? Excellent. Okay, so I want you to try number 11. When you come back, we'll do it together. Okay, we're back. And there you go. So if you got that one right, excellent. Try number 12. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so that was just a little bit of review on the distributive property and multiplying binomials. Now we're going to review the most important types of factoring. It's very common for students not to have enough practice, and sometimes students don't even know some of these types of factoring methods or these factoring scenarios. When you take your calculus course, you're going to be expected to know all three of these. These are the absolute minimum that you need when it comes to the types of factoring scenarios that you need to know. But there are other types of factoring. For example, when you use grouping, or when you factor an expression like this, or when you have more than one variable, or the sum or difference of two cubes. If you're not very familiar with these, that's not really that big of a problem. But if you're not familiar with these, that suggests that your instruction in previous courses was not really what it should have been. So again, the purpose is not to teach you this. The purpose is just to give you a warning that you need to know this, and if you don't, you may be in the wrong course. So let's factor. It says here, factor the expressions below. Write the type of factoring used in the margin. So for this problem, we're going to factor a GCF, a greatest common factor, and that's going to be 2x squared. And we need to write what's left after we factor that GCF. So we're going to have 5x to the third power minus 4x to the second power plus 8x plus 3. And we can check our work by using the distribution property and going backwards. So 2x squared times 5x cubed is 10x to the fifth power, so we know that's correct, and we can check the other ones using the same method. 2x squared times negative 4x squared is negative 8x to the fourth, that's what we got, and so on and so forth. So we factored a GCF, and I want you to try a problem like that. The type of factoring is going to be GCF factoring again. So see if you can find the greatest common factor and simplify this, or factor the expression. When you come back, we'll do it together. Okay, we're back. So that is one of the most common types of factoring that you're going to be expected to know in calculus. Okay, so now we're going on to quadratic, or factoring in the scenario where you have a quadratic. So remember, when you have a variable squared, a variable that's not squared, it's raised to the first power, and then a number without a variable, that's a quadratic expression. And not all quadratic expressions are easily factored, but these are going to be easily factored. So we ask, what are two numbers such that when we multiply them we get negative 3, but when we add them we get 2? What are two numbers such that when you multiply them you get negative 3, but when you add them you get 2? So that's going to be 3 and negative 1. When you add 3 and negative 1 you get 2. When you multiply 3 and negative 1 you get negative 3. So there you go. This is really, really basic stuff. This is stuff that you should know really, really well. If you've never seen this, or you are having a lot of problems with this, again, I suggest you're in the wrong course. So let's try another one of those. Now, by the way, if you wanted to check, you can FOIL this, or use the box method, whatever method you want to use, x and 3, x and negative 1. And if you get to the original expression, then you know you did it correctly. So use the FOIL acronym, first terms, outside terms, inside terms, last terms, and add them up, and you should get the original expression. So we're going to factor this. What two numbers multiply to 15 and add up to negative 8? Well, that's going to be negative 5 and negative 3. Negative 5 times negative 3 is positive 15, and negative 3 plus negative 5 is negative 8. So again, this is just review. Try number 17. When you come back, we'll do it together. Okay, we're back. Okay, try number 18. When you come back, we'll do it together. Okay, we're back. Negative 7 plus 1 is negative 6, and negative 7 times 1 is negative 7. Okay, so you're also going to have the situation where you have a coefficient in front of the x squared term. In that situation, it's more difficult to factor. So instead of x and x, you write 3x and x, because 3 times 1 is 3, right? Then we just have to choose some numbers and see what works. So negative 2 times 4 is negative 8, right? But we don't know for sure that it's actually going to work, so we have to multiply this out and see if we get the original expression. So I'm going to use the FOIL acronym. First terms, outside terms, inside terms, and then last terms. And we can see when we combine these we get 10x. That's not correct. So what do? Well, we just switch the numbers. And now if we FOIL, we get positive 2, so it's not correct. So we just have to change the sign here to positive. We got the right number, we just didn't get the right sign, so we just changed the signs. Change this number to a negative, or this sign to a negative. And it looks like that's it. So again, when you have a coefficient here, it's much more involved, or it's a little bit more difficult to factor that. So let's try number 20. Now we can try 4x and x, or we can try 2x and 2x, because 2 times 2 is 4 and 4 times 1 is 4. I'm going to try 5 and 5. 5 times 5 is 25. And if we FOIL that out, we get 20x in the middle, so that actually doesn't work. So I'm going to try 4x and x, and that actually works when we FOIL that out. Again, you have to multiply it using either the box method or the FOIL method, and you can see that the inner terms add up to 25x. So there you go. So go ahead and try number 21. Again, the purpose of this is not to teach you this information. You should already know the information. The purpose of this is to just get you started, or get your mind jump started. So try number 21. When you come back, we'll do it together. Okay, we're back, and I just realized I've been forgetting to write the type of factoring. So this is quadratic. That's quadratic factoring. This is quadratic factoring. And this is quadratic, so we've done a number of quadratic problems. This is also quadratic, but it's the more difficult type of quadratic. And this is the more difficult type of quadratic also. So again, that was factoring a quadratic. If you got that right, good. Try number 22. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so we factored a greatest common factor, and we factored the quadratic expression. And so now we're going to do the third type of factoring, which is factoring the difference of two squares. We have a square here and we have a square here. Now why is 9 called a square? Well, because you can write it as 3 squared. So when you have the difference of two squares, meaning you're subtracting the squares, you can just square root each term and then write a plus and a minus. And there you go. So again, that's something that you just need to know how to do. It's just one of the fundamental types of factoring. So try number 24. When you come back, we'll do it together. Okay, we're back. So if you got that right, good. So for number 25, we have a coefficient on the x squared, but we still do the problem in the same way. We just square root each term. So the square root of 64 is 8. And the square root of 25 is 5. And we write a plus and a minus. And to check this, you can actually FOIL this out, multiply it, and you should get to the original expression. Okay, so go ahead and try number 26. When you come back, we'll do it together. Okay, we're back. And again, we just write a plus and a minus. So there you go. Sorry, that's kind of scrunched in there. So if you got that right, excellent. So we did the 3 types of factoring: the GCF factoring, the quadratic factoring, and the difference of two squares factoring. Let me write dots here. We need an S at the end there, difference of two squares. I'm going to make a little more room here, so we have dots there too. Okay, so again, this is something that your teachers should have focused on. If they didn't, then that means that could be a big problem. some students may know this, they don't know it really well, but they have seen it before. And if that's the case, then that may be okay. It's just you're going to have some problems if you don't really have a very good fluency with this. Some students may have never seen some of this stuff at all. That's not okay at all. That means you're probably in the wrong course. Okay, so another topic that is something that students typically struggle with, but is absolutely critical and essential for success in upper mathematics, is the root formulas. It's so common for students to really not have a grasp of this information, although you should know it by now in the curriculum. It may not be your fault that your teachers didn't really go over it much, but you need to have a fluency with these rules, and it is so common for students to really not even be able to use these formulas. So there's really just two formulas. There's a multiplication formula and a division formula, and it works for any index. 99% of the time, the index that we use is 2. So square roots. 2 meaning square roots. Now, when you write a square root, you don't write a 2 for the index. That's just assumed to be 2, right? But when you write any other root, you write the actual number. So let's use the product rule. The product rule tells us that we can multiply. If we have the same index and we're multiplying roots, then we can multiply what's inside the root and combine it into one root. So very, very important property. And so here we have the square root of x squared, because we can multiply what's inside the roots, right? But then when you square root x squared, you get x. Now, if you're starting with this expression, then you would have to write the absolute value of x, because we don't know if x is negative or positive. But when we start with this expression, we assume that x is positive, because these would have to be imaginary numbers if x were negative. And we assume that those are not imaginary numbers because we don't have an I there. Okay, so we use the product rule. Now let's use the division rule. The division rule tells us that when we find the root of some fraction, that's equal to the root of the numerator divided by the root of the denominator. Again, a very important rule that so many students do not know. So the cube root of 8 is 2, the cube root of 27 is 3. There you go. I don't know why I wrote a fourth root there. That should be a cube root. There you go. So 2 times 2 times 2 is 8, and 3 times 3 times 3 is 27. So go ahead and try number 30. Use the product rule, or the multiplication rule. When you come back, we'll do it together. Okay, we're back. If you got that right, good. Try number 31. Okay, we're back. So notice that when we multiply square roots and the inside parts are the same, we can just get rid of the root. Because multiplying a number by itself is the same thing as squaring a number, but squaring a number is the opposite of square rooting a number, so you just get back to 7. Okay, try number 32. When you come back, we'll do it together. Alright, we're back. So we got that right. Excellent. So go ahead and try number 33. When you come back, we'll do it together. You're going to use the division rule. Okay, we're back. If you got that right. Excellent. So these are the root formulas. Now, the stuff that we're learning here is not everything that you need to know. You probably need to have a much greater fluency with these formulas than what we're doing here. The purpose of this is just to show you, or it's to be a warning that if you don't know this information, you're certainly not going to be able to do the calculus. Okay, so now we're going to pull out a perfect square. And we're going to use the, well, first we're just going to factor. That's 9 times 2. But then we're going to go backwards with the multiplication rule. And we're actually going to separate into 2 roots. And the square root of 9 is 3. And then we can just get rid of the dot. Again, if you've never seen this before, that's a big problem. This is something that is very common that you're going to be expected to know how to do. Pull out a perfect square out of a root. So here we have a cube root, so we're looking for a perfect cube. You don't really see this situation very often, but 8 is a perfect cube. We're going to use the multiplication rule and separate into 2 roots. And then the cube root of 8 is actually 2. 2 times 2 times 2 is 8. And then we can get rid of the dot. We don't really need the dot. When you write the numbers right next to each other, that's assumed to be, or when you write a number next to a root, that's assumed to be a number multiplied by the root. So, I want you to get a picture of all this information here and try number 36. Pull out the perfect square. When you come back, we'll do it together. Okay, we're back. And of course, we don't really have to write the dot. So there you go. All right, so do you know how to do that? Or do you not know how to do that? That's a big question. If you don't know how to do it, well, there's different levels of scenarios here. If you've never seen it, that's the worst scenario. If it's kind of familiar, but you don't really know how to do it, that's the next best scenario, but it's still not a very good scenario. If you know it, but you're kind of rusty, that's okay. It'd be better if you were more fluent, but most students are in that kind of situation when it comes to assuming that you fulfilled the prerequisites and assuming that you did all the work that you were supposed to do in your previous classes. Most students are in that situation where they've seen it, but they're a little rusty with this stuff. So go ahead and try number 37. When you come back, we'll do it together. Okay, we're back. 4 is not something raised to the 4th power. So if you got that right, excellent. Okay, so now we're going to use the multiplication rule and the division rule in this problem in order to rationalize the denominator. Remember, you can't have a root in a denominator. In one of the first problems that we did today, we had a root in the denominator, but it was a variable, and so in that situation, teachers are usually more forgiving. But when you have a regular number that we know is an irrational number, because we actually know what the number is, it's 6, this is an irrational number, we know for sure, and you're expected to know how to rationalize that denominator. So we're going to use the fundamental principle of fractions and multiply both sides of the fraction by root 6. Now, the numerator is just going to be 7 root 6. We can just leave it like that. We're going to use the multiplication rule, which tells us that you can put those together in one root. So you get root 36. And the square root of 36 is obviously 6. So you see how we got rid of the root? We changed the form of this yellow fraction to the blue fraction. It's the same fraction. It's just written in a different form where we don't have a denominator that's an irrational number. You're expected to be able to do that. That's especially useful when we analyze trigonometric ratios. So let's try another one. Now we have a more complicated situation because we have a perfect square inside this root. So let's first take out the perfect square. 12 is 4 times 3. And then we're going to use the multiplication rule to break that into a product of two roots. And then we're going to find the square root of 4, which is 2. And of course, the 2's just cancel out. And you're left with negative 1 over root 3. The problem is we still have a root in the denominator. We simplified the fraction quite a bit. And I know students are going to ask, well, what do I do first? Do I pull out the perfect square or do I rationalize the denominator? Pulling out the perfect square is actually better because it makes it easier for us to rationalize the denominator. The numbers are going to be smaller. So now we need to rationalize the denominator. So I'm going to multiply both sides of the denominator by root 3 using the fundamental principle of fractions. And so we get negative root 3 over root 3 times 3. And by the way, you don't have to show these steps. If you know what you're doing, you can just do this very, very quickly. And root 9 is 3. So we used the multiplication rule here to pull out a perfect square. And we used the multiplication rule again to rationalize the denominator. So I want you to take a picture of numbers 38 and 39. So I want you to try number 40. You're going to rationalize the denominator. We can't have a root in the denominator. So try number 40. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. So go ahead and try number 41. Again, we're rationalizing the denominator. We don't want a root in the denominator. But I suggest pulling a perfect square out of the root first. Okay, try number 41. When you come back, we'll do it together. Okay, we're back. The 2's cancel out. We're left with root 2. So you're going to be expected to do that. And your calculus teacher is not going to tell you how to do it. If you know what you're doing, you can go from here to here in maybe 2 steps. Some students may even try to do that in their head, but most students, it would probably take about 2 steps. You don't have to show all this stuff. So don't think that you need to really show all this stuff. If you know how to do this, then you can just jump to the answer. Now, why am I showing all the steps? Well, because there's no point in me doing this unless I show the steps, right? Okay, so let's try another one. Here we have the square root of an entire fraction. And so we're going to use the division rule. We have the square root of 18 over the square root of 5. That's the division rule. Again, there's only 2 rules with square roots, or any kind of roots. There's the multiplication rule and the division rule. That's it. So now we're going to pull out a perfect square by changing root 18 to root 9 times 2. And then we'll use the multiplication rule. And root 9 is 3. But we still have a perfect square in the denominator, so we have to deal with that situation. So we're going to multiply both sides of the fraction by root 5 in order to rationalize the denominator. And we're going to have to use the multiplication rule again. So do you see how you have to know these rules? This is why this stuff is so important. You're just going to use it again and again and again and again in the math curriculum. And if you don't have a good fluency with this stuff, how are you going to be able to do this? So now the square root of 25 is 5. So there you go. Okay, so I want you to try a problem like that. Try number 43. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so far we covered the exponent rules, and we covered the most important types of factoring, and we did a little bit on roots. Now again, a lot of students may say, well, you're not covering this enough. We need to, you need to do full instruction on each one of these topics. But again, that's not the point of this. If you need full instruction on each one of these topics, then you're in the wrong course. This is stuff that you should know before entering this course. We're not going to do full instruction on that. You can go to previous courses in the curriculum to get full instruction on that. Again, math prerequisites are strongly enforced. So you need to know that material before coming into calculus, because there's just not enough time. Well, it doesn't have anything to do with time. It just has to do with the fact that this course is about learning calculus. It's not about learning algebra or, or trigonometry or geometry, the prerequisite courses. So now we're going to go over some trigonometry. Now, in previous courses, we mostly used degree units for the measures of angles, but in calculus, radian units are most often used. So it's very important that we understand radian units, and we have ways of converting back and forth between degree units and radian units that you can look at here, using something that we call the factor label method in science. But really, you can understand radians just by comparing these two figures here. Pi is defined to be equal to 180 degrees. And so if that's true, then if you divide pi by 2, that should be the same thing as 180 divided by 2, which is, you guessed it, 90 degrees. If you divide pi by 3, that should be the same thing as dividing 180 by 3. So what do you get when you divide 180 by 3? 60 degrees. So pi over 3 is 60 degrees. See, this is really not that hard. When you divide 180 by 4, you get 45 degrees. So pi over 4 is 180 divided by 4, which is 45 degrees. So understanding radians is not as difficult as it may seem. Now, if pi over 3 is 60 degrees, then 2 pi over 3 should be 60 degrees times 2, right? Because you're just multiplying pi over 3 by 2 to get 2 pi over 3. So if pi over 3 is 60, 2 pi over 3 must be 60 times 2, which is 120. If pi over 4 is 45 degrees, then 3 pi over 4 must be 45 degrees times 3, which is 135 degrees. So again, this is really not that difficult. But because pi is defined to be 180 degrees, we use this conversion factor. If you want to convert from degrees to radians, then we multiply by pi over 180. If you want to convert from radians to degrees, then you multiply by 180 over pi. But just be aware that we're going to primarily be using radians. Again, we're not doing full instruction on this information. We're just kind of reviewing things. Also, of course, we have the 6 trigonometric ratios. Get a picture of all this information. We use SOHCAHTOA down here to help us. Remember the at least the first 3 trigonometric ratios. So get a picture of that information. Also, you need to know the special triangles. This is all very basic information. Now again, I would not be surprised at all if some of this stuff you don't know, because again, in most curricula around the world, instructors don't teach this. They don't focus on it enough, and some instructors don't even teach it at all. It's not your fault. It's just that's the purpose of this class, is to show you what you're supposed to know before entering this class. So I don't have any control over what you did previously with other teachers. If you want to make sure that you're ready, you can take my courses, and then I can guarantee. That's the whole purpose for my courses, is so that there's a guarantee that you're ready for this course. But I can't guarantee, because I don't know what you learned when it comes to your other your previous courses from other schools. Okay, so I want you to get a picture of this information here, and that's all the basic trig that we need to get started here reviewing. So we're going to find the value of each expression. Trigonometry is crucial in calculus. It is absolutely crucial. So first thing we need to do is figure out what pi over 3 is. Well, if you look at your chart that I just showed you, that's just 60 degrees. Pi is 180 degrees. You divide by 3, you get 60. So it's the same thing as 60 degrees. So we need to find sine 60 degrees. So 60 degrees terminates in the first quadrant. We're going to draw the angle in what we call standard position, where the vertex of the angle is at the origin, and the initial side is on the positive side of the x-axis. This is the terminal side of the angle. Okay, so we can see that this is going to be a 30, 60, 90 degree triangle. And if you know your special triangles, you know we call this side x, this side is x root 3, and this side is 2x. That's just, those are the relationships between the sides of 30, 60, 90 degree triangles. Again, you're expected to know that. So now we just find the side opposite the reference, the purple reference angle, divided by the hypotenuse. The longest side of a right triangle is called the hypotenuse, remember that? And these sides are called the legs. Then we just cancel out the x's, and we're left with root 3 over 2. So you're expected to be able to find these values without a calculator. You could easily find this value with a calculator if you change your calculator into radian mode, but unfortunately you're expected to be able to find these values without a calculator. Okay, so now we're going to find cosine 5 pi over 4. First thing we need to know is, what is 5 pi over 4? Well, pi over 4 is 45 degrees. Well, first of all, let's start from the beginning. Pi is 180, right? Divide 180 by 4, you get 45 degrees. Multiply 45 degrees by 5, and you get 225 degrees. So this is the same thing as cosine 225 degrees. So we're going to draw the angle. So we're going to go all the way around to 225. And the reference angle, the purple reference angle, is 45 degrees. I'm going to make that a different color. I'll make that red. And that means that this angle has to be 45 degrees because of the triangle sum theorem. And how did I find 45 here? Well, because remember, this yellow angle is 180. This angle is 180, so you subtract 180 from 225 and you get the purple leftover angle. Okay, so we're dealing with a 45, 45, 90 degree triangle. Again, if you look at your 45, 45, 90 degree triangle theorem, that tells us that if this side is x, then the hypotenuse is x root 2. And this side is x also. These sides are the same in a 45, 45, 90 degree triangle. But I've made a big mistake. The mistake that I made was that those x's have to be negative. They're both negative because you're to the left of the y-axis and you're under the x-axis. Okay, so now cosine is defined to be the side that's adjacent to the purple angle divided by the hypotenuse. And so the x's cancel out, you're left with negative 1 over root 2. But this is where your root formulas really come in. You're expected to be able to change this to negative root 2 over 2, and your calculus teacher is not going to show you how to do that. It's just assume that you know how to do that because we want to rationalize the denominator. Now, some calculus teachers may not care. They may just allow you to leave it like that. But this is really considered the proper way to leave your answer. Okay. So let's try another one. So pi, again, is 180. Pi divided by 6 is 180 divided by 6, which is 30 degrees. And then 13 pi over 6 is 30 times 13, which is 390. So cotangent negative 13 pi over 6 is the same thing as cotangent negative 390 degrees. So because it's a negative angle, we're going to start, well, we always start on the x-axis, the positive x-axis, and we're going to rotate clockwise instead of counterclockwise. So we have 360 degrees, and then we're going to go a little bit past. So we went 30 degrees past a full rotation. So that is 30 degrees. That's the reference angle, which means that this other angle must be 60 degrees. So we're dealing with a 30, 60, 90 degree triangle. And so our 30, 60, 90 degree triangle theorem tells us that if the side opposite 30 is x, then the side opposite 60 should be x root 3, and the hypotenuse should be 2x. All right, those are the relationships between the sides. But I made a big mistake. This side has to be negative. Okay? So now we're ready to go. Cotangent is the adjacent side of the purple reference angle divided by the opposite side of the purple reference angle. All right, so we're left with negative root 3. So this is the type of trigonometry that you're going to be expected to know. Let's try another one. And by the way, I forgot to write that angle. That's negative 390 degrees. Okay, so now we have 2 pi over 3. First thing we need to do is find, figure out what that angle is. So pi is 180. 180 divided by 3 is 60, and 60 times 2 is 120. So that's the same thing as cosecant 120 degrees. So let's draw the angle. So 120 degrees would be about there, somewhere around there. And there's our triangle. So the reference angle is going to be whatever this purple angle is. So that's the leftover. A half rotation is 180. Subtract the pink angle, which is 120, and you get 60 degrees. So the reference angle is 60 degrees. And that means this angle, of course, is 30 degrees. So we're dealing with a 30, 60, 90 degree triangle. Based on our theorem, we know that if this side is x, then this side is x root 3, and this side is 2x, because it's a 30, 60, 90 degree triangle. But again, I've made an error. This side needs to be negative, because it's to the left of the y-axis. Now this side is positive because it's above the x-axis. Okay, so now we're ready to go. So cosecant is defined to be the side, or it's the hypotenuse divided by the side that's opposite the purple reference angle. So that's x root 3. So it turns out we didn't really care that that's negative because we're not even using that. Okay, so x's cancel out, and we're left with 2 over root 3, but we have to rationalize the denominator, so we're left with 2 root 3 over 3. Again, notice how you're just expected to do that without any explanation. So I'm going to give you a lot of opportunities to do these problems and really get your mind jump started. So take a picture of this information. Take a picture of this information, and I want you to use numbers 44 through 47 to help you with 48. So the first thing you need to do is to figure out what this angle is in degrees, so you can have an idea of what you're dealing with. So pi is 180. So if you take 180 divided by 4, you get 45, and 45 times 3 is what? So do that problem, and when you come back, we'll attempt it together. Okay, we're back. So if you got that right, excellent. So I want you to try number 49, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, go ahead and try number 50, and when you come back, we'll do it together. All right, we're back. So there you go. If you got that right, excellent. Go ahead and try number 51. When you come back, we'll do it together. Okay, we're back. And so our final answer is -2. So if you got that right, excellent. Okay, so now I want you to try number 52, and when you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Okay, go ahead and try problem number 53, and when you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, so go ahead and try number 54. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, go ahead and try number 55, and when you come back, we'll do it together. Okay, we're back. Okay, so if you got those right, excellent. So we had to use the special triangles to find the values of trigonometric ratios without a calculator. If you need a calculator, then that's really just something that's easy to do. It's not really necessary to go over that. You just enter it in the calculator, you got your answer. So all the angles that we used so far were angles that did not land on the x or y axis. If the angles actually terminate, when I say land, I mean when they terminate on the x or y axis, then you get what we call a quadrantal angle. So when you have quadrantal angles, for example, if you had a 90-degree angle, then this triangle would get closer and closer to the y-axis because we're trying to get to a 90-degree angle, right? We're trying to make this angle go all the way to 90. And so what happens is the triangle actually collapses. It actually disappears. If you have a collapsed triangle, that's called a quadrantal angle. Same thing happens when you go to 180 or 270 or 0. So in those situations, it doesn't really make sense to analyze the value with a triangle. Mathematicians just define those values using this curve. So this curve works for all angles, but especially the quadrantal angles. That's these green points. So when you have quadrantal angles, you just want to use this curve. It's just the easiest way to do it, at least with the sine function. We have a different curve for the cosine function and a different curve for the tangent and all the other ratios. So I want to make it clear that you're expected to memorize all 6 of these graphs. You're going to have situations where you'll be given something like sine pi, and you'll be asked to find the value of that without a calculator. Well, how do you do that? The only way to do it is to picture this graph in your mind and think about where the input is on the x-axis, and then find the corresponding y value of the point on the graph. So that tells you that sine pi is 0. Now, if you can't picture this graph in your mind because you don't have it memorized, then you'll be asked to find something like sine pi, and then you'll just stare at that while other students find the answer immediately and go on to the next problem. So I'm just letting you know, in the same way that you're expected to memorize these special triangles so that you can do problems like this, you're also going to be expected to memorize every single one of these graphs so that you can find the values of trigonometric functions when the angles are quadrantal. Now, there are going to be situations where you have to use a calculator. For example, sine pi over 5, there's no way to really find that value without a calculator because you need upper mathematics to do that. So sometimes you'll need a calculator, but you'll be expected to find values like sine pi over 2, or cosine negative pi, or tangent 0. These are all quadrantal angles. In the same way that you're expected to use the special triangles to find values of these expressions without a calculator, you're also expected to memorize these graphs so you can find these values without a calculator. So is that clear? That's the way it's going to be in calculus in all upper math courses. So I'm giving you these graphs. You have the graph right in front of you, but the point I'm trying to make here is you're expected to have this memorized in your head. I shouldn't even need to show you this. Is that clear? This should be in your head. You need to memorize it, because you're going to be given values like this and nobody's going to show you this graph. You're just expected to have that in your head. So let's say you want to find sine 3 pi over 2. Well, that's the same thing as sine 270 degrees, because pi is 180. Divided by 2, you get 90, and 90 times 3 is 270. So you have to find sine 270 degrees. But you don't really have to convert to degrees, because I've given you the radian version of this graph. But just be aware that this is 90 degrees, 180 degrees, 270 degrees, 360 degrees. These numbers are multiples of 90. So you can think about it however you want. You can think of it in radians or degrees, but you have to use the graph regardless to find the answer. So we find 3 pi over 2 on the x-axis, and then we ask, well, what is the corresponding y value of the point on the graph? And that is -1. So there you go. 2 pi, that's 360 degrees. Again, pi is 180, so 2 times 180 is 360. So what is the y value of the corresponding point in the graph? Well, that's 0. And then sine 0, that means we don't move out at all on the x-axis. What is the y value of that point? 0. So we're just looking for the y values of the points on the graph. Negative pi over 2 would be here, even though it doesn't show it. What is the corresponding y value of the point on the graph? That is -1. Again, this is all review. You should have seen this information in previous classes. So negative pi, that's going to be here. What is the y value of that point? That's 0. Again, we're dealing with collapsed triangles. And 5 pi over 2, that's 5 times pi over 2, so that's 1, 2, 3, 4, 5. And the y value there of the point on the curve is 1. So there you go. So you're going to use the cosine curve. Go ahead and try numbers 62 through 67. And when you come back, we'll do it together. Alright, we're back. So cosine pi over 2, that's 0. Cosine pi is -1. Cosine 3 pi over 2 is 0. And cosine 2 pi is 1. Cosine 0 is 1. Cosine negative pi over 2 is 0. Again, these are the y values of the points on the graph. So if you got those right, good. Now I want you to understand that not only do you have to memorize the special triangles, the 45-45-90 triangle and the 30-60-90 triangle, and not only do you have to memorize the special angles and the 6 trigonometric functions, but you also have to memorize these curves. There's 6 curves, and I know that's kind of a tall order, but that's just part of the math curriculum. You have to have all these memorized. So now we have the secant curve. Now, in order to draw the secant curve, you first draw the cosine curve, which looks like this, and then you draw the red parts based on that. So that's just how you can remember that. So secant pi, that's -1. That's the y value of this corresponding point here. secant pi over 2 is actually undefined because there's a yellow asymptote there. Secant negative pi over 2 is also undefined. So why don't you try number 71 through 73. When you come back, we'll do it together. Okay, we're back. 1, undefined, and negative 1. So if you got those right, good. Okay, let's try the cosecant curve. Cosecant pi over 2, that's just the y value of the corresponding point at pi over 2, that's 1. Cosecant pi is undefined, there's a yellow asymptote there. Cosecant 3 pi over 2 is negative 1. And I want you to try numbers 77 through 79. When you come back, we'll do it together. Okay, we're back. So there's a yellow asymptote there. That's negative 1. And this is undefined. There's a yellow asymptote there. So you're going to be expected to have these curves memorized. Also the tangent curve. So tangent pi, that's 0. Is the y value of this corresponding point here. Tangent pi over 2 is undefined. There's a yellow asymptote there. Tangent 0 is 0. And I want you to try numbers 83 through 85. When you come back, we'll do it together. Okay, we're back. So tangent negative pi is 0. Tangent negative 3 pi over 2 is undefined. There's a yellow asymptote there. Tangent 2 pi is 0. So if you got those right, good. You're also going to be expected to have the cotangent curve memorized. So cotangent pi over 2, that is 0. Cotangent pi, undefined. And try numbers 88 through 90. When you come back, we'll do them together. Alright, we're back. Cotangent negative pi over 2, that's defined to be 0. But that's the y value of this point here. Cotangent 0 is undefined because there's a yellow asymptote there. Cotangent 3 pi over 2 is 0. So if you got those right, excellent. So this was not everything that you're really required to know to prepare for calculus. It's just some of the things, some of the most important things. You need to know the exponent rules, the 3 most important types of factoring, the root formulas, the basic trigonometry, the special triangles, and the curves, the graphs of the trigonometric functions. These are fundamental things that you need to know. So that was the class today. We're going to do some more precalculus review in the next class. And then after that, we're going to get on to the calculus. But this is, again, just to jumpstart your brain and to be a warning for you that you need to be fairly well versed in this type of math in order to do well in this course. So that was the class today. If you'd like to take screenshots of all the work that we did, go ahead and do that now. Here's screenshot number 1 and screenshot number 2 and number 3 and 4 and number 5 and number 6, number 7, and number 8, and number 9, and number 10. But don't go before you get the homework. Now, it's very important to understand that the homework is not optional. It is a requirement. A lot of students may say, well, I just like to pass on the homework, but you're not going to pass on the homework. You're going to do it completely, neatly, and keep it in order in your binder. And you must do it correctly. If you get the wrong answer, you have to check your answer. And if you get the wrong answer, then you have to go back and fix what you did wrong. So here's screenshot number 1 and screenshot number 2 and screenshot number 3, number 4, number 5, and here's the answers to the homework. Again, it's not enough just to attempt the homework, it must be done correctly, so check all your answers. So get that homework done completely and correctly and neatly, and I'll look forward to seeing you in the next class.